Hey everyone, in this video we're going to be going through the whole of Edexcel GCSE chemistry key concepts. So this is the absolute foundation knowledge you need for chemistry. If you'd like to follow along with this video, over on my website you can download my notes and other resources. Okay, so this is an atom, and inside the nucleus of the atom we have protons and neutrons. And then in the shells outside of the nucleus we have electrons. So we have three subatomic particles: protons, neutrons, and electrons. Protons have a charge of +1, so they're positive. Neutrons have a charge of 0, so they're neutral, they have no charge. And electrons have a charge of -1, so they're negative. So you can think P for positive, neutron sounds like neutral, and then you have to remember that electrons are negative. Now protons also have a mass of 1. Now when we're talking about the mass of subatomic particles, we have no units. Protons just have a mass of 1. Neutrons also have a mass of 1, and then electrons have a mass that is too small to count. They're so tiny that we just say they have no mass. Now, atoms always have the same number of protons and electrons. Now, protons are positive and electrons are negative, and if they've got the same number, these cancel out evenly, making the overall atom neutral. So every element on the periodic table has its own unique atom, and it's the amount of these subatomic particles that make these atoms up. Now over time, different scientists have had different ideas about the atom. One of the earliest models of the atom was Dalton's billiard ball, and he said that atoms were solid spheres making up everything around us. J.J. Thomson then created the plum pudding model, and he said that atoms were a positive sphere with negative electrons. And then we have the model that we use today, and this is Rutherford's planetary model, and he added the shells and the nucleus. So these are the three main models of the atom that you need to know. So an isotope is a different version of an element's atom with a different number of neutrons. So we remember that neutrons are the subatomic particles with a mass of 1 and a charge of 0. So if we have a different number of neutrons, this means that the mass of the atom is going to change. Now, it's really important to remember that only the number of neutrons change. The number of protons and electrons don't change, because that would mean the element's atom would change. If we just change the neutrons, it's still the same element, but just a different version. Now here we have two isotopes of carbon, carbon 13 and carbon 12. And the 13 and 12 is the carbon's mass number. So the mass number tells us how heavy the atom is. Remember we said that neutrons have a mass of 1 and protons have a mass of 1. If we add all the protons and neutrons together, we get the mass number. So this bottom number is the proton number, or the atomic number, so it tells us how many protons we have. If we subtract it from the overall mass number, we get the number of neutrons. So carbon 12 has 6 neutrons, and carbon 13 has 7 neutrons. So we have two isotopes of carbon with different numbers of neutrons. So if all elements have different isotopes, how do we know what number to put on the periodic table? We can't have two versions of carbon on it. This is where relative atomic mass come in. And relative atomic mass is an average of all of the isotopes of the element. So let's look at this with a question. It says copper 63 and copper 65 are two isotopes of copper. So this number after it is their mass number. Copper 63 has an abundance of 69.2%. and copper 65 has an abundance of 30.8%. Calculate the relative atomic mass of copper. So we're first going to write out the different isotopes and the amount of them. So copper 63 has an abundance of 69.2%, and copper 65 has an abundance of 30.8%. So to work this out, we multiply the mass by the percent of each isotope, add them together and divide them up by 100. So we do the mass times the percent of each isotope, then add them together and divide the whole thing by 100. Now the periodic table is the way that we organise all of the elements that we know. And it's sorted out into groups which go down in columns and periods which go along in rows. Now over on this side of the periodic table we have all of the metals, and over on this side, just after this staircase, we have all of the non-metals. Now the group number that an element is in tells us the number of electrons in the outer shell. And the period number tells us the number of shells the atom has. Now the elements are organised by atomic number and the properties that they have. So elements that are near each other on the periodic table will have similar properties. Now we can use the periodic table to find a number of things. We already know that the group number tells us the electrons in the outer shell, and the period number tells us the shells. But we have the mass number, which tells us how heavy the atom is, the symbol, which tells us what atom we're looking at, and then the atomic number. And the atomic number tells us how many protons the atom has. Now if we know the number of protons the atom has, we also know the number of electrons, because they always have the same number of protons and electrons. Now the first periodic table was created by a scientist called Mendeleev. Now he wasn't the first scientist to group elements and sort them together, but he was the first scientist to realise that we hadn't discovered all of the elements. So he left gaps in his table as predictions. And he did this based on the characteristics and properties of the elements we had already found. So we can see here he's got question marks and gaps for missing elements. And his table was also arranged by atomic mass, not atomic number. Now an ionic bond is a bond between a metal and a non-metal. Now atoms bond to get a full outer shell. If atoms don't have a full outer shell, so that's 2 electrons in their first shell and 8 in all of the others. If atoms don't have a full outer shell, they're not very happy, they're not stable. So an ion is a charged particle. And this is formed by the loss or gain of electrons. So when atoms form an ionic bond, they lose or gain some of their electrons. So remember that electrons are negatively charged. If an atom loses some of its electrons, it's losing some negative charges. Now we have the same number of protons and electrons in an atom, but if we lose some electrons, we have more protons, so we have more positive charges. So if an atom loses them, we form a positive ion, which is a cation. And then if we gain electrons, we're gaining some negative charges, so we have more electrons than protons, so we form a negative ion, which is an anion. So let's look at an example of an ionic bond happening. So we have sodium, which is our metal, and chlorine, which is our non-metal. So to get a full outer shell, sodium can do one of 2 things. It can gain 7 electrons to get a full outer shell, or it can lose 1. Now it's much easier for sodium to just lose 1 electron, so that's what it's going to do. It loses 1 electron. So this electron is lost and given out. Now because it's lost an electron, it's going to have a +1 charge. So sodium is going to form a positive ion, and this is going to be a cation. So now for chlorine to get a full outer shell, it needs to lose 7 electrons or gain 1. Now we already have this 1 electron that's been floating around from the sodium. So chlorine gains this electron. So sodium has given its electron to chlorine. So it gains 1 electron. So this forms a -1 charge. So chlorine forms a negative ion. And this is an anion. Now it's not always as simple as this. Sometimes we have multiple atoms involved. Now oxygen needs 2 electrons to fill up its outside shell because it only has 6. Now each lithium atom can only give 1 electron because it only has 1 in its outside shell. So oxygen needs to bond with 2 lithium atoms to get its 2 electrons. So this lithium gives 1 electron to the oxygen, and this lithium gives 1 electron to the oxygen, meaning that oxygen gains 2 electrons, forming a 2- charge, because it's gained 2 electrons, so it's now a 2- charge, and each lithium loses an electron, so it forms a +1 charge each. So we have 2 lithiums, so we have Li2 and 1 oxygen, which is O. So that is this ionic compound. Now ionic compounds form a giant crystal lattice. And this word lattice just means it has a regular structure. Now the way these ions come together is that there are strong electrostatic forces between the positive and negative. So if we say in this diagram all of the green ones are cations, they're positive ions, and all the purple ones are anions, so they're negative ions. There are really strong forces between all of these holding them together. So these electrostatic forces are strong forces between positive and negative ions. Now this giant crystal lattice means that ionic compounds have high melting and boiling points. And this is because we need a lot of energy to overcome these strong electrostatic forces. And ionic compounds can also conduct electricity when they're molten or dissolved, and this is so that the ions can move freely and conduct a current. Now when ionic compounds bond, we might want to write an ionic equation to show what's happening to each ion. So let's start with the normal equation. We have hydrochloric acid, HCl, bonding with sodium hydroxide, which is NaOH, to make sodium chloride, which is NaCl, and H2O. So this is the normal equation. Now the first thing we want to do is split our ionic compounds, which is our HCl, sodium hydroxide and sodium chloride. We'll look at water later. Water's bonded in a different way, and split them up into their ions. So we have H+, Cl-, Na+, OH-, Na+, and then Cl-. Now you might be wondering why I've given OH- one charge, and this is because it's a polyatomic ion. Some ions, like OH-, have a charge on the whole compound, so these are just ones that you need to remember and know. Now when we're looking at ionic equations, we're going to remove the spectator ions, and these are ions that don't change. So H+ goes from being H+ to being part of the water molecule, so that has changed. But this Cl- stays the same before and after, so this doesn't change. We can just remove this from the equation. And that's the same as NH+. NH+ starts as an ion and finishes an ion, so we can just remove this from the equation. So we end up with H+ add OH- equals H2O, because H2O hasn't changed, it hasn't split up into ions. Now a covalent bond is a bond between non-metals, and it's a shared pair of electrons. So let's look at these hydrogen atoms. They each have one electron in their outer shell, but they want two, so they come together and share their electrons in the middle. And these electrons whiz around both atoms, meaning that both atoms technically have two electrons in their outer shell. So this is the shared pair. Now sometimes they need to give two pairs of electrons to get the full outer shell. So this double bond between oxygen, we have two pairs of electrons being given, so that each oxygen has 8 in its outer shell. And this is a double bond, because we have two pairs. So within covalent molecules, we have strong covalent bonds, and these are between the atoms in the molecules. So these are very strong. But between covalent molecules entirely, we have weak intermolecular forces. And because these are so weak, these can be easily overcome. So the covalent molecules tend to have very low boiling points. They can turn into gases very easily. So here are two allotropes of carbon. These are giant covalent molecules, and allotropes are different structures containing the exact same element, but they come together in different patterns or shapes to form different things. So we have diamond and graphite. So diamond is very hard and strong, and this is because it has this triangular and pyramid shape. Any pressure that's put on one atom is spread evenly across all of the other atoms, and this makes it very useful for lining the edges of tools, as it's a very durable material. However, diamond cannot conduct electricity. And this is because each carbon atom is bonded to 4 other carbon atoms, so there are no free electrons to be able to delocalize and conduct a current. Now graphite is organised in layers, and these can slide over each other. So this makes graphite a very good lubricant. And graphite can conduct electricity, because every atom is only bonded to 3 other carbon atoms, so that we have this spare electron that can delocalise and become a flow of electricity. Now the final type of bonding is a metallic bond. And this is caused by metal atoms giving up their electrons. These electrons just delocalise. And because the electrons have left, this forms positive metal ions. And again, we have strong electrostatic forces between all of these particles. This type of bonding gives metals very high melting points. Now, a mole isn't just a furry little creature that lives in the ground, it's also the name of a special number. And this number is 6.02 times 10 to the power of 23. Now, you don't need to memorise this number, but you need to be able to recognise that this is 1 mole. And this special number links mass to the number of atoms in a sample. Now we can calculate the number of moles by dividing the sample, so how much of the thing we have, divided by the mass of its compound. So the best way to explain this is by showing a few questions. So let's look at this. How many magnesium atoms are there in 60 grams of magnesium? Now we know that moles are found by the sample over mass of compound. So first we have the sample, and we have 60 grams of our magnesium. And now we need to find the mass of the compound. Now this just means how much magnesium atoms weigh, so its atomic mass is 24. So if we divide these together, we get 2.5. So we have 2.5 moles. Now the question isn't asking us how many moles we have, it's asking how many atoms we have. So now we need to times the number of moles by the special number. So 6.02 times 10 to the power of 23. And this gets us 1.505 times 10 to the 24. So when looking at moles, we use a lot of standard form, which is writing really big or really small numbers to a power of 10 like this. Now relative formula mass is the total mass of a compound. So what I mean by this is we can use the periodic table to find the mass of carbon and hydrogen, but we can't use it to find the mass of this whole molecule, which is methane. So we can add them together. So if carbon has a mass of 12 and hydrogen has a mass of 1. Now we only have one carbon atom, so we have the 12, but we have 4 hydrogen atoms, so we need to multiply the mass of hydrogen by 4. And then if we add this together, we can get the mass. Empirical formula is the simplest ratio of all the numbers in a compound. So if we have this molecule here, which is glucose, we have C6H12O6. Now this is quite a big molecule, these numbers are quite big. So sometimes we want to simplify it down, so we only have to work with smaller numbers. Now we want to find the highest common factor between all of these, and that is 6. So if we divide 6 by 6, we get 1, so we get C1. If we divide 12 by 6, we get 2, so we have H2. And then if we divide 6 by 6 again, we get 1, so we have 6,1H2O1. Now in chemistry, we don't really like the number 1, so we're going to get rid of that and just say 6H2O. So this is the empirical formula of glucose. So now we've looked at moles, relative formula mass, and empirical formula. Some questions ask for some of them combined. So let's look at this question. A gas is made from 60% oxygen and 40% sulfur. Find the empirical formula. So the first thing we're going to do is write out what we know from the question. So we have sulfur, and we have 40% of it, and we have oxygen, and we have 60% of it. Now, another bit of useful information is the mass number of each of these elements. So sulfur has a mass of 32, and oxygen has a mass of 16. Now we're going to find the number of moles. So we can find the moles by dividing the sample by the mass, which is already here. So if we divide these, we get 1.25 and 3.75. And now we want to use all of this information to find the empirical formula. So we're going to divide these both by the smallest number, which is 1.25. So if we do 1.25 divided by 1.25, which equals 1, and then if we do 3.75 divided by 1.25, we get 3. So now we can use this as a ratio. So we had 1 and 3. So that means we've got 1 sulfur for every 3 oxygens. There are a lot of steps when looking at this, but just remember, always write down what you know from the question, then the mass number, then the moles, and then if you're trying to find the empirical formula, use it to figure out the ratio. So here's another question. A student heats 1.08 grams of magnesium ribbon so that it forms magnesium oxide. The total mass of magnesium oxide formed was 1.80 grams. Calculate the empirical formula of magnesium oxide. So again, there's quite a lot going on in this question, but let's write out what we know. So we know we're looking at the elements magnesium and oxygen. So let's figure out how much we've got of each of these. So it says we have 1.08 grams of magnesium. But it doesn't directly tell us how much oxygen we have. It only tells us that the whole molecule of magnesium oxide is 1.80. So if we subtract 1.08 from 1.80, we get the amount of oxygen, which is 0.72. So we have 0.72 grams of oxygen. So let's write the mass numbers out. The mass of magnesium is 24, and this is just the number from the periodic table, and the mass of oxygen is 16. Now we want to find the number of moles, so we divide these together. So we get 0.045 and 0.045. So if we divide these both by the smallest number, which they both happen to be the same, so 0.045 divided by 0.045, and this gets us 1. So both of these are 1, and this is our ratio. So for every 1 magnesium, we have 1 oxygen. So here's the last example question. Compound X has the empirical formula C2H6N. The relative formula mass of compound X is 88. What is the molecular formula of compound X? So this is asking us to do the same thing, but backwards. So we have the empirical formula, and we have the relative formula mass, so the mass of the whole compound, and we want to find the normal formula, the molecular formula. So the first thing we're going to do is find the mass of the empirical formula. So we have C2H6N, and we want to find the mass of this. So carbon has a mass of 12, and we have 2 of them. Hydrogen has a mass of 1, and we have 6 of them. And nitrogen has a mass of 14, and we have 1 of them. So if we figure these out and then add them all together, we'll get the mass of the empirical formula. So we get 44. So the mass of the empirical formula is 44. Now we want to divide the relative formula mass we have in the question by the answer we just got. So we're going to do 88 divided by 44. So this gets us 2. And then we're going to multiply all the numbers in the empirical formula by the number we've just got. So we start with C2H6N4. We want to times all of these numbers by 2. So we end up with C4H12N2. And this is the molecular formula of the compound, and this is what the question wanted us to find. If this video helped with your chemistry revision, please subscribe to my channel and check out the other videos I have.